the difference of squares quadratic. Here are some examples of difference of squares. In each of these quadratics, we have patterns happening, whereas each term is a perfect square. This is 2x times 2x. This is 3 times 3. This is x times x, 5 times 5, 3x times 3x, and 8 times 8. So notice every single term is itself a square. The other part of the pattern is the operation between these two squares is subtraction. You'll recall that difference is the mathematical term for subtraction. So what we have here is subtraction of two perfect squares. One perfect square minus another. The difference of squares is a special form of a quadratic because there's a pattern that exists in order to factor it every time. And the factoring comes from the fact that we don't have an x term. We're used to these quadratic trinomials where we have an x squared and then some number of x and then a number. X squared, some number of x, and then a number. We don't have that here, although we kind of do. In each of these examples, we have 0x. So if we were to look at this example, and imagine we were trying to factor this trinomial, 0x doesn't exist, but we can say we have 0x. We could apply the knowledge we already have for factoring quadratic trinomials. We have a quadratic trinomial. The first term's coefficient is 1. And so all we need to do is find the values that multiply up to this number that add up to this number. And it's going to work out the same way every time, which is that this is a perfect square. So we have 5 times 5 to get there, but you'll notice it's negative. So one has to be positive and one has to be negative. And those numbers will always add up to 0. So that's the pattern that we're relying upon in order to factor our difference of two squares. If we were to then factor this into our double sets of parentheses, we get x plus 5 and x minus 5. Again, the reason why this is a special form of a quadratic for factoring is because it looks like you would get a quadratic trinomial here, but our middle terms cancel. If we were to FOIL this to check our work, we would get x times negative 5 and 5 times x. That's negative 5x and positive 5x. Those are our middle terms that cancel up to 0x, and therefore we just have our original difference of squares quadratic. So it turns out it's pretty simple to factor these. That's what's great about them. All we do is we find the square root of the first term, and we plug that in the beginning of each set of parentheses. The square root of 9x squared is 3x, so it goes here and here. The square root of 64 is 8, so it goes here and here. And since we're working with a difference of squares, we've established that one of these is plus and one of these is minus. Again, difference of squares, perfect square, subtraction. Factoring it gives us two sets of parentheses. The square root of the first term, the square root of 4x squared is 2x, goes in the front. The square root of the second term, the square root of 9 is 3, goes in the second. And since this is negative, we're going to give one of these a plus and one of these a minus. This pattern always exists for difference of squares, and so it's a very easy special quadratic to factor. First you recognize it, then you take the square root of the first term, put it in here and here, and the square root of the second term, and put it in here and here. To accommodate the subtraction, one is subtraction and